Think about all the choices you make every day. You know, what to eat, which route to take, what to watch. But what if the stakes were way, way higher? What if you had to teach a machine how to make the best possible choice, not just once, but over and over again, in a world where you're never quite sure what's going to happen next? Well, that's the code we're cracking today. I mean, seriously, think about it. How do you do that? This is one of the biggest questions in AI. How do you get a machine to think strategically when the future is always changing? Your basic if this, then that rules just aren't going to cut it. You need a system that can actually handle uncertainty.
Well, it all starts by creating a map. Not a map of roads and cities, but a map of possibilities. Now, take a look at this diagram. I know it might look a little complicated at first, but it's really just a picture of every possible situation, every choice, every random chance, and every single consequence. This is how we start to make sense of a complex world. And this map, it's not just some abstract idea. It has a real name, the Markov Decision Process, or MDP for short. And it's an incredibly powerful mathematical framework that gives us the exact tools we need to tackle these kinds of problems head-on.
So, at its heart, an MDP is just a way to model making a whole series of decisions when you can't be 100% sure of the outcome. Think of it like a board game where some of your moves are decided by rolling the dice. The MDP is basically the official rulebook for that game.
Let's break down that name because it sounds a little intimidating. The Markov part comes from something called the Markov property. It's really just a fancy way of saying that to make the best decision, all you need to know is where you are right now, not the whole long journey that got you here. It's memoryless. And the decision process part? That's exactly what it sounds like. Some agent is actively making choices that are going to shape its future.
And you know, don't think this is some brand new tech fad. MDPs have actually been around since the 1950s, starting out in a field called operations research. But their true power has really been unleashed now, in the modern era. Today, they are the absolute backbone of everything from economics and ecology to healthcare and, of course, to the most advanced AI.
So, how do we actually build one of these decision-making maps? Well, it's probably simpler than you think. Every single MDP, no matter how complex it seems, is made up of just 4 fundamental ingredients.
In the world of math, they call it a 4-tuple, but we can just call it S, A, P, and R. So let's dive in and see what each of these letters actually stands for, and we'll use our map from before to help us out.
First up, we've got S for states. A state is simply a specific situation the agent can find itself in. On our map here, the states are those green circles, S0, S1, and S2. In the real world, a state could be anything, a robot's exact location, the current price of a stock, you name it.
Okay, so you're in a state. Now what? Well, that's where A for actions comes in. From any given state, the agent has a bunch of choices it can make. On our diagram, those are the orange circles, A0 and A1. For a robot, an action could be move forward or pick something up. Now this is where the uncertainty kicks in. P stands for transition probabilities. This tells us the chance of ending up in a new state after we take an action. So, if we take action A0 from state S0, there's a 70% chance we land in S1, but there's also a 30% chance we end up over in S2 instead. This is literally that roll of the dice we were talking about.
And finally, we have R for rewards. This is the crucial feedback that tells our agent if it's doing a good job. A positive number, like that +5, is like a pat on the back. A negative number, like -1, is a little nudge saying, hey, maybe try something different. The agent's entire goal, its whole mission, is to rack up as many of these reward points as it possibly can.
Okay, so we have our map, we have our rules, we've got our states, actions, probabilities, and rewards. But what's the point? What's the end game here? What are we actually trying to do with all this? The goal is to find something called a policy. You can just think of it as a complete strategy guide or a rule book. For every single situation you could ever be in, the policy tells you exactly what to do. But we don't want just any policy. We are hunting for the optimal policy, the absolute best strategy that will get us the most reward in the long run.
And this right here really nails it. We're not just chasing after the next immediate reward. We're playing the long game. Sometimes you have to make a small sacrifice right now to set yourself up for a much bigger payoff later on. The optimal policy gets that. It's always thinking ahead.
So, how in the world do we find this perfect strategy? Well, computers use some really clever algorithms to do the heavy lifting. One way, called value iteration, focuses on calculating the long-term value of being in every single state. Another way, policy iteration, just starts with a totally random plan and then keeps improving it, bit by bit, until it's perfect.
All right, now let's connect the dots. Because this isn't just a math exercise. This framework is the engine that is powering one of the most incredible fields in artificial intelligence today, reinforcement learning.
And this is the absolute key. MDPs are the rulebook, and reinforcement learning is the player. The MDP lays out the entire game, the board, the pieces, the rules. Then the reinforcement learning agent gets to play that game, thousands, even millions of times, learning from its mistakes until it masters that optimal strategy.
To really see this in action, let's look at a classic AI challenge, the pole balancing problem. The goal is super simple. Just move a cart left or right to keep a pole balanced upright for as long as you can. It sounds easy, but trust me, it's a real test.
We can frame this whole challenge as an MDP. The state, that's the pole's angle, how fast it's moving, the cart's position, and its speed. The actions? Simple. Just push left or push right. The reward? You get a little point, a +1, for every single moment that pole stays up. And the optimal policy? That is the perfect, elegant balancing act that the AI learns entirely through trial and error.
So, let's bring it all home. What's the big takeaway here? Why does all of this matter so much?
It's this. The MDP is like a universal translator. It allows us to take almost any messy, real-world problem that involves making choices, from winning a game to managing an investment portfolio to running a factory, and translate it into a clean, formal language that a machine can actually understand and solve. And that leaves us with a pretty mind-bending question, doesn't it? If this framework can be used for basically any problem that involves choices and consequences, what are the limits? The real question isn't what machines can learn anymore. It's what are we going to dare to teach them to solve next?